We're going to be talking about the Hardy-Weinberg Modeling Lab, which is Investigation 2 from the new lab manual. I'm going to walk you through some of the theory of what we're trying to do in the lab first, and then I'm going to actually open up a spreadsheet and walk you through some of the commands that you'll need to be able to execute in order to see what's going on in the lab. So what we're trying to do here is we're just trying to show, we're trying to simulate a sexually reproducing population. We can use spreadsheets to generate large numbers of individuals in the population so that we can see what happens with very large populations and very small populations. Ultimately, what we're really trying to do is simulate different evolutionary forces and see what their effect is. We're also going to be trying to simulate what occurs when there is no evolutionary force acting on a population. So we're trying to see if we can truly find a Hardy-Weinberg equilibrium and what that shows. So in this, we're just trying to simulate one gene in this population to keep things simple. We're going to assume that it's a simple Mendelian style gene, which means that it will just have two alleles, one dominant, one recessive. Typically, we've represented dominant and recessive with an uppercase and lowercase letter, but as it turns out, sometimes spreadsheets have difficulty counting something that's uppercase versus lowercase. So for the simplicity of our spreadsheet, we're just going to make the dominant letter A, or the dominant allele A, and the recessive allele B. Remember that P represents, in the Hardy-Weinberg equations, P represents the frequency or the percentage of all the alleles that are dominant, and Q represents the percentage of all the alleles in the gene pool that are recessive. So you can use lots of different software to run this simulation. I'm going to run mine in just a minute in Microsoft Excel. However, you're welcome to, if you are at home and you'd like to practice this before coming in for lab, you can also, if you have a Google account, just get on Google Docs online and kind of use the spreadsheet there. All of the commands are by and large the same, with one exception that I'll talk about. And you could potentially download a piece of software called OpenOffice as well if you wanted to use sort of an offline version. The only problem I have with Google Docs is that all of the processing takes place online. So if you potentially have a slow internet account, it can get bogged down with some of the volume of data that we're going to put into our spreadsheet. So especially in class, you're welcome to practice on Google Docs at home, but please, when you come to class, I want to make sure you use Microsoft Excel. So I'm going to switch over to Microsoft Excel here, and we're going to run through some of the commands that they suggest in the lab manual. So we're here in Microsoft Excel now, and we're ready to begin. So the first thing I actually recommend you do is you click in this little area in between column A and row 1. If you click that, it selects the whole entire spreadsheet. If you just go over to alignment up here and center everything, that'll just make everything a little nicer and a little easier to see in relation to each other. Then we're ready to enter P and Q. So by the way, I'm doing what's recommended on pages S30 through S36 of your lab manual. So if you'd like to follow along, you can reference those instructions. We have to input what the initial dominant allele frequency is. So we have to give it a number between 0 and 1. I would recommend, as you and your partner work on this, that you choose a variety of different initial allele frequencies to see if that has any effect. So if I were to do 0.3, then we could just simply say that Q is equal to 0.7, since they both have to add up to be 1. But I would encourage you to use formulas all the way through this, because if you use formulas, you can get the spreadsheet to do a lot of your calculation for you. So how do you do formulas? You could either write in the cell itself, or you can kind of go up to this little box, the function box up here. You always start functions with an equals sign. And in this case, to just tell it that you'd want to subtract 1 from whatever is in the cell above it, you could just do 1 minus, and you just want to indicate which cell that is by either clicking on the cell, or you could just write in B1. And that will simply execute that function. And notice here that it put in 0.7 for me. So if I change P throughout the course of my investigation to say like 0.8, notice how it updates Q for me. I'm going to go ahead and make it 0.5 just for the sake of this activity here at first. Your lab manual is then going to suggest that you play with the random function, so equal sign rand just in some kind of cell. And if you do rand, you need to do open parentheses, close parentheses. And if you hit enter, what you'll find is that it generates a number in between 0 and 1 truly at random. If you hit F9 with your keyboard, you'll see that it gets you to recalculate for you. I actually can't do that with this recording software that I'm using, so I'm afraid I'm going to be unable to show you that. But please try that at home and make sure you see that it truly generates a very random number in between 0 and 1. And that's a very powerful function, because we're going to be able to use that to randomly generate gametes that either have the dominant or the recessive allele according to how frequent or how pervasive or how widespread those alleles might be in the overall gene pool. So we can use that randomness to correctly generate alleles with the following formula. So I'm going to put it over here in column C, row 4. I'm going to create what's called an if statement. So equal sign if. And in parentheses, I need to tell it what to assess with the if statement first. So I'm going to say if you generate a number at random, so if rand, open parentheses, close parentheses. I'm going to say if whatever that number is less than, so a less than sign, or equal to, equal sign right afterwards, whatever is in column B1. Let's click that, because then if we change it later, it will update accordingly. I also recommend that you go ahead and put a $sign in between B and 1. That's a little fancy for what the reason why we're doing that, but it'll essentially make sure that it copies correctly when we copy it later. So if a random number is generated that is less than that number, remember that the random is generating a number between 0 and 1. So if p is 0.5, then we would expect the random number to be less than it half the time and greater than it half the time. So all we need to do then with the rest of our if statement is we need to tell Excel what to do in both cases. If it truly is less than the value that's up there, then we want it to go ahead and put a text letter A to indicate to go ahead and put the dominant allele in that case. And if it's greater than the value that's in P, then we want it to go ahead and put in a text letter that is the recessive allele B. Whenever you put in text letters for these statements, you want to put text in quotation marks. That's how it knows that it's a text that it's putting in there. Then hit close parentheses. That's a very complicated formula, but essentially it's going to generate gametes at random. So hit enter, and it will probably show up as A or B. If you were to hit F9 again, which I would encourage you to do, which I can't do with this recording software, it should pop up maybe A half the time, and it should be B about half the time. But another way we can show that is we can generate a lot of gametes by simply copying this formula down this column with many cells. So an easy way to copy the formula is to click on this black square at the bottom right when you've got that cell selected. So this little square right here. Click on it, hold your left mouse button down, and drag down to however many cells you want to copy it to, and just release your click, and notice that it will generate that for us. So notice here that I've created quite a lot of gametes now, and about half of them are B, and about half of them are A. And if I were to change my P up here, let's say I make it something like 0.9, notice that the vast majority here should now be A, and very few of them should be B. And if I were to make P very low, the exact opposite thing should happen. So notice that this spreadsheet is doing exactly what we want it to do. Each gamete is truly randomly derived, but the overall population is fairly reflective of the overall P and Q that we've inputted above. So I'm going to change it back to 0.5. Remember that we need 2 gametes in order to create new offspring. So I also want this column over here to have gametes generated at random. So all I'm going to do is I'm going to go up to my formula bar, and I'm just going to copy the entire formula using copy up here. And then I'm just going to hit enter so that my formula stays. And then I'm just going to paste in the cell next to it, and it will copy the same formula. I can use this square, click, hold down the left mouse button, drag it all the way down, release the left mouse button, and it will generate all these gametes for us. We could, if we wanted to, you could hold down the shift key and select the cells, both cells above it. Use this merge button up here and just kind of give it a title. So these are our gametes. If you would like, that's fine. And then we just want to show what happens when whatever gametes that are next to each other form when they fertilize or make a zygote. So how can we tell Microsoft Excel to combine whatever is in the boxes next to each other? Well, that's just a formula that has a very fancy name called concatenate. So concatenate will tell us, it's just a formula that gets you to put together the text that's in two text boxes. So we just need to indicate the two cells that contain the text we want to combine with commas in between. So I'm telling it to concatenate parentheses the cells that are in C4, comma, D4. I'm going to have to write that in because it isn't showing it right now. Close parentheses and hit enter, and it will go ahead and put those together for us. I'm going to click on the square at the bottom right and drag it down so that it goes ahead and puts together what's in each row for me. And notice that I've got a bunch of different zygotes of 3 different genotypes. Some of them are homozygous dominant, some of them are heterozygous, and some of them are homozygous recessive. Oops. I'm just going to hit cancel there. So is there any way that we can get the spreadsheet to kind of count how many of there are of each for us? There is. So we could kind of think about counting each genotype by creating little labels. And how can we get it to count it for us? Well, we're going to use if statements again. So if we did equals sign if, I want to know if whatever is in this zygote box over here, click on it, if that is equal to the text value of AA. And whenever it's in text, you need to put it in quote marks. You need to tell it what to do if it is indeed AA and what to do if it is not AA. Well, if it is the genotype that we're trying to count in this column, we just want to put a 1. And if it isn't, we want it to put a 0 to not count it. So that's all we need to do, that formula. Hit enter. Notice that over here it's actually heterozygous this time around. By the way, notice that every time you kind of do something new in this spreadsheet, it will sort of, the randomness will recalculate a new random number. So you might notice that these things will jump around a lot, but that's okay. Here it's actually heterozygous, so it's not counting it. It just put a 0. I'm going to drag this down by dragging the box again. And notice that it's just putting a 1 by the cases where it is indeed homozygous dominant, so that I can kind of know that I've done that correctly. It's pretty easy to count BB. I'm going to skip AB for just a second. So let's do an if statement to count all the BBs. So if that zygote box equals text, so quote marks, BB, end quote, put a 1 in there if it is BB, and put a 0 in there if it's not BB. So close the parentheses, hit enter, and drag your formula down. Okay? Hopefully you've got it to count BBs. So how can we get it to count heterozygotes? So it's a little trickier here, but not too much. The only trick is that there's 2 ways you could potentially be heterozygous. You could either be AB and be heterozygous, or BA. So in our if formula, we need it to count both possibilities. So how do we start? We're going to start the same way. So if, parentheses, that zygote box equals, let's pick one of them, so quote marks AB. Then if it is indeed AB, then I want it to put a 1, so comma. What if it isn't AB? Well, I want to give it another chance to see if it's BA. So I'm actually going to, for the false part of the equation, I'm going to create a second if statement. If, parentheses, that same cell equals quote marks BA, quote marks, still put a 1 by it. And if it's false for kind of both of those, put 0 and close the parentheses on both. So if you put that in correctly, you should be able to drag it down, and you should be able to see that it's counting it for BA as it also is for AB. So we've got a count. Maybe we could go a few columns over now and total those. So how many total homozygous dominant, heterozygous, and homozygous recessive organisms are there? How can we get this to add up all the ones in these columns? Well, we can simply use the sum tool. So equals sum, and we just need to give it a range. So what I like to do is just click on the first cell in that column, hold down the shift key, click the last cell in the column, and hit enter. And it will add those for us. So how do I add the heterozygotes? The same way. Click, shift, hold it, click on the last cell. Okay, and let's do that with the homozygous recessives as well. Sum, parentheses, click on the first cell, hold down shift, click on the last cell, enter. and it's adding all of these together. So we've got now sort of a sense of how many of each genotype there will be in the next generation, but we also want to know how many alleles there are total in the next generation. So how can we use the numbers that we've already generated to figure out how many of each allele there are? Well, it's actually pretty easy to do that with a formula too, because how many A alleles are there? Well, we can just ask it to consider how many organisms are homozygous dominant by clicking on that box. If you're homozygous dominant, you have 2 copies of the A allele. So let's multiply that number of organisms times 2 to get us the alleles. And we also want to add in how many organisms are heterozygous because they have 1 A allele. So if I hit enter, I've got the A alleles, and I can do the same thing for B alleles by finding out how many organisms are homozygous recessive, multiplying by 2, and adding how many organisms are heterozygous because they have 1 B allele as well. So I've got my alleles. And then to really calculate the next generation, I need to figure out what the P is for the next generation and what my new Q is for the next generation. So how do I calculate that? Well, P is just what percent of the total alleles are dominant. So I know that I have that many alleles that are dominant in my numerator, and I want to divide that and just make it a fraction of the total number of alleles. So I want to make a parentheses because I'm going to add this to that, and that will give me P. How do I get Q? Same way. I know that there are that many total alleles in the gene pool, and I want to make that a fraction of the total. So again, parentheses in the denominator, that added to that. And I've got my, if I've done all this, I've got an Excel to do all the calculations for me. Again, you could hit F9, I can't do that, but you could hit F9 and you could see it generate lots of different results for this first generation. And then what we're ultimately interested in doing is, because evolution involves multiple generations, I'm going to want you to create maybe at least 5 generations of all this data so that you can see what really happens from generation to generation to generation. Now, if you're thinking, oh my gosh, do I have to do all of that again? The answer is no. The beauty of getting this spreadsheet to do a lot of the calculation for us is we can simply copy and paste everything we've done so far into the next generation. So how am I going to do that? I'm just going to click the column A up here, and I'm going to hold Shift down and go all the way over to M, where I did kind of my data. I'm going to hit Copy up here. I might just leave one column in between generations so that I don't get confused, and I'm going to click Paste. And notice if I scroll over that everything is already in there for us. Beautiful. The only thing we need to do is remember that in the first generation we had to input what P was, so it just copied that from the first generation. But what I actually want to do is I want to make sure that this P considered up here simply is equals whatever it calculated in the end of the first generation down here. So if I do that, then it will automatically calculate what it is next, and it will run that set of numbers. And if I wanted to create a third generation, I'm just going to go over here to generation 2, start in column O, click, hold Shift, click over to my last column, copy, go one column over, paste, and there's generation 3. This time I don't even need to tell it what to do with P because it assumes it's doing the same thing it did last time with generation 2. So it's actually got the information in there for us. So if I wanted to create 2 more generations, then I just need to continue to copy and paste. Hold Shift down, copy, go a column over, paste, generation 4. Do the same thing. Go over to generation 4, hold, Shift, copy everything, paste everything. And very, very quickly, you've got 5 generations worth of data. Okay, so beautiful thing there, and I'd love for you guys, once you get 5 generations of data, to hit F9 quite a bit. I'd love for you to see what happens when the population is fairly small like this. The one other thing your lab manual recommends you do is maybe you want to make some bar graphs of certain features. So they suggest you make a bar graph of how many different genotypes there are as you go. So how can you make a very quick and simple bar graph? You can just click on the labels and the numbers, So maybe start in the cell up here, hit Shift, click down to this, go over to the Insert tab on Microsoft Excel and find Column. Click that, maybe just make it a 2D column, unless you want to go super fancy, and it's automatically made a bar graph for you. Very simple. So you can just drag that down here so it doesn't get in the way of your data. And sometimes when you hit F9, it will automatically update the graph for you too. You can see kind of what's going on from generation to generation graph-wise as well. So what have we done so far? I'm going to scroll all the way over to the beginning part of my chart here. I've created 5 generations of data based on a fairly small population. So at this point, I would certainly encourage you to save. You probably want to save well beforehand. But notice here that you've actually got 3 worksheets down here too. So if you wanted to modify this, you wouldn't have to completely change it so that you sort of wipe away your old data. What I'd recommend is that you keep everything you've done on this worksheet. Maybe you right-click on sheet 1 and click Rename so that you can say this is what happens when there's a small population. I'm going from 4 to 20 here, so that's actually an N of 17 total. Maybe you want to record that as well. And then let's say you wanted to make your population much bigger, something that I will encourage you to do to investigate what happens when the population size is much larger. All we would need to do is click on this all over here in between A and 1, hit Copy. Then I could click over to Sheet 2, and I could click Paste. And then I can kind of mess with the population to make it much bigger without wiping away all of my data for the small population. How can I make this bigger? I can just tell Microsoft Excel to extend the formula for all 3 of these columns. In fact, I could do all of it at once by just clicking this first cell and holding down Shift, going all the way over here, and just telling it to, by clicking on this black square at the bottom here, let's take it all the way down to say 1,000. So I've got it down to 1,000. I'm holding down the left mouse button, and then when I let go, it will automatically create data for all of this as well. So I've just gone from 4 to 1,000. That's a much bigger population. I do need to get my numbers over here updated though, because currently if I click on the total AA count, it's just adding them from 4 to 20 like the last spreadsheet. So if I make that 1,000 instead, it will update the numbers for me. I'm going to do that for each of my genotypes. And all of my numbers are up to date. I can simply copy this generation now by copying the columns. Copy. I can go over here to the next generation, paste. And I can do this for multiple generations too. So once you really get the foundation started, a lot of your work is finished, and you can use the spreadsheet and copy formulas to quickly generate new data about larger populations or smaller. So that's really all I wanted to show you in this video demonstration, how to get yourself basically set up. We want you to simulate what happens in a small population and in a large population with different starting allele frequencies. And then you'll have the opportunity to maybe tweak this and maybe see if you guys can figure out how to simulate other forces like, say, natural selection, sexual selection, maybe gene flow. So thanks for listening, and we'll see you in lab.